So in the last class, we were discussing about the design of a one-way slab, and we have seen the complete procedure that we should adopt for designing the slab. And we have two sections mainly, that is limit state of flexure, as well as we have to check for shear also. So normally in the case of slabs, it will be automatically safe in the case of shear, because we have seen that tau b was less than tau c by 2. Okay, so in the previous problem we have designed a simply supported beam. So today we will do one thing, we will just fastly go through the procedure of design for a cantilever beam also. After that you can practice. I hope you are able to see the problem, right?
Yes, sir.
So basically, this is a problem on one of the cantilever slabs. This we usually have in our balconies, and maybe in some projected portions, maybe they are present in some of the buildings. So we should understand that we have to design that also. So the main thing is again remain same here also. That is, when we have a cantilever, the tension will be on top side. When the load is acting from top to bottom, the tension will be on top side and compression will be on the bottom side. So when you design for flexure, you have to provide that reinforcement on top side, okay, not on the bottom part of your slab. So that is the main thing. Anyway, let's take up this problem. So this problem states that design a cantilever slab for an overhanging of 1.25 meters. That is, we are having this cantilevered portion over a length of 1.25 meters from the base of the support. The imposed load on the slab consists of 1 Newton per meter square of live load, and weight of finishes is 800 Newton per meter square. So this is directly given in the question. If it is not given in the question, when you perform the design of slab, please assume some values for this, and please have a knowledge on the range of values that we usually take in the case of imposed load and the finishes. Okay, so normally for finishes we will take it as maybe 1 kilonewton per meter square. And similarly, imposed load is actually selected based on the type of building or the type of room which we are designing. Anyway, for the sake of examination, you can take it from 1 to 1 kilonewton per meter square, or 2 kilonewton per meter square. Please note this will be 1 kilonewton per meter square, not 1 Newton per meter square. That may be a mistake here. Anyway, let's see that. And we are supposed to use M20 grade concrete and Fe14 grade steel. So let's see the data that was given in the question. The clear span is given as 1.25 that we have seen. Imposed load is, as I mentioned, it is 1 kilonewton per meter square or 1000 Newton per meter square. Then weight of finishes is given as 0.8 kilonewton per meter square or 800 Newton per meter square. Then we have the grade of concrete, grade of steel, and these are the data given in the question. So in the previous problem, we actually have started with the control of deflection, but again, after getting the value from the control of deflection, we have directly assumed a value. Anyway, here in this case, I have just avoided those steps. Those steps are not necessary. I hope I have said the same thing there also. You can directly make an assumption. Only thing is that in a later stage, you should prove that this assumption is true. Okay, so here I am directly assuming that my overall depth of the slab be 130 millimeters. I am going to design a slab having a thickness of 130 millimeters or 13 centimeters. So from this, what I am doing is that I am just assuming a clear cover for slab of 15 millimeters, and I am going to assume a diameter of the main reinforcement as 8 millimeters. So basically my effective depth will be the overall depth minus clear cover minus half of the diameter of the main reinforcement. So this will give me around 111 millimeters as my effective depth. Okay, so I am proceeding with the same value. Now what I am doing is I am just going to calculate the design bending moment and shear force as we have done in the previous problem. So for this, first of all, I have to calculate the self weight, and this is the thickness. And again, please do remember the width will be assumed as 1000 millimeters. Slab, in the case of slabs, one-way slab, we will normally design it as a beam having a width of 1 meter. Okay, so for that reason, the self weight will be equal to 0.13 into 1, that covers the area of cross section, multiplied by unit weight of your concrete. So that will give you 3250 Newton per meter. So please take care of the units. So in the previous problem, I think we have substituted as 25. but here we have substituted as 25,000 because we are calculating the final answer in terms of Newton per meter, not in terms of kilonewton per meter. So please take care of these things. These are areas where usually students commit mistake. That is why I am again and again repeating these things. So please take care of the units. So here we have obtained a value of 3250 Newton per meter. Now I have an imposed load of 1000 Newton per meter. Then we have weight of finishes as 800 Newton per meter. Therefore, the total load acting is the sum of all these things. So that will constitute around 5050 newtons per meter. Now we have to factor that load. We are using limit state method, so we have to use design load or the factored load. So we have to multiply it with respect to a factor of safety, and you know that in the case of a limit state method, it is 1.5. So 1.5 times 5050, that will give you 7575 Newton per meter. So this will be the final design load. So based on this load, we have to now calculate our bending moment. So factored bending moment mu is equal to WL square by 2. So please remember, this is cantilever, so this will be the maximum bending moment. Okay, so basically you will be having, so I hope you know this, right? I need not explain how to calculate, how you obtain WL square by 2, and that you have already studied in your MOS. Anyway, so basically this cantilever is carrying a UDL throughout the length, which is having the intensity of 7575. So first of all, you have to convert that UDL into a point load which is acting at the center, and we have L by 2 distance from the support, because this point load is acting at the center. So W into L, that will give the point load multiplied by L by 2. That is our WL square by 2. That is the maximum bending moment coming at the support. Now shear force is again equal to W into L. Okay, so that is, and again please note this 1.30. In the question it is given as 1.25 is your clear span. So how we obtain this 1.30? That is your effective span. How you calculate effective span? That should be done as per IS 456, and we have specific clauses mentioned there regarding calculation of effective span. In the case of simply supported beam, we have seen that it was either the center to center distance between the supports or clear span plus effective depth. But in the case of cantilever, there is slight variation in that. Is anyone remembering how to calculate the effective span in the case of a cantilever? It will be the clear span plus half that of effective depth. Say we have it here. So 22.2 is regarding your effective span. First of all, we are provided with details regarding simply supported beam or slab. Then going down, we have details of cantilever. So in the case of cantilever, they have mentioned it as the effective length of a cantilever shall be taken as its length to the face of the support plus half the effective depth. Okay, plus half the effective depth, except where it forms the end of a continuous beam, where the length to the center of the support shall be taken. So in this problem, it is not mentioned that this slab is actually forming the end of a continuous slab or something. So basically we can assume that it is an independent slab which is just projecting from the support. So let's take the first condition, that is the length to the face of the support, that is a clear span, plus half the effective depth. And in this case, effective depth was obtained as 111, right? Here we have already calculated that it is obtained as 111, and so it will be equal to the clear span, that is 1.25 plus 0.111 divided by 2. That will give you a value around 1.30. When approximated, it will come around a value of 1.30. So substitute these values and calculate the value of factored bending moment as well as factored shear force. So once that is done, we have to first of all check. First of all, based on the condition of over reinforced beams, that is using the relation corresponding to balance section, we have to check the depth of the section. So you already know this, we have repeated this many times. So you are utilizing this equation, you substitute the value of calculated bending moment here and find the value of this D from this equation, and you can get the value of X limit by D based on the grade of concrete and from the table given in IS 456, and I suggest you to by heart those three values. We have different values for FE 250, FE 415 as well as FE 500. You can refer the code during your examination, but that will take up your time. So please note that and try to remember it. It is very easy, only three values, right? So from this expression, you can calculate the value of D, and here you can see that it is obtained at as. So in the case of balance section, the D will be 48.16 millimeters. But the value of effective depth that we have provided is 111, millimeter, which is far more higher than the minimum requirement. So it is safe. So we can proceed with this depth. So it is safe in consideration of over reinforced section. So basically our section, since we have a larger depth, what is our inference? Our section is a under reinforced section. Now we have to calculate the amount of steel that should be provided to take up the required moment. So we have already calculated the moment. So substitute the value of moment here and use this expression for under reinforced section. And from this expression, you have to calculate the value of AST. That is the amount of steel that should be provided. So once you do that by substituting all other values is known to you. So you just, and please again remember the value of B here is 1000 millimeters, okay, or 1 meter. So please substitute that correctly. Then find the value of AST. So once you get the value of AST, what you can do is that you can assume we have already made this assumption of 8 millimeter diameter bars to be provided as our main reinforcement when we calculated the effective depth from the overall depth in the initial part of this problem. So we are taking the same diameter. Now the spacing of the bar is equal to 1000 multiplied by area of cross section of a single bar having diameter 8 millimeters divided by the area required. So here the area required is 154.42. So by substituting that, we will obtain the spacing as 325.35 millimeters. So this is the exact spacing that is required. So what we will do is that we will just round it down. So what I am doing here is provide 8 mm diameter bars at 300 millimeter center to center. And one more thing is that we have to check for, say, sometimes you may be rounding it to 320 millimeters, but we have some clause given in 23.3.3 regarding the maximum permitted spacing between the longitudinal bars. That will restrict your spacing to 300 or 3 times the thickness in the case of main reinforcement. So based on that clause, maybe they have reduced the spacing and they have provided 8 mm diameter bars at 300 millimeters center to center. Now, the actual area which is provided, we have to find. Suppose this was the required spacing, but we have provided a smaller spacing. So we have to calculate the actual area which is now provided. So the provided steel area is equal to 1000 multiplied by again area of cross section of a single bar divided by the spacing, and that will give you 167.47 millimeters. The actual AST requirement was 154, but we are now providing 167.47 millimeters because we have reduced the spacing. Now the percentage of area of the steel should be calculated by dividing this by the cross-sectional dimension of your concrete. So this is the steel area divided by 1000 into the effective depth. That will give you, I think it is better to substitute rather than effective depth, you can substitute the overall depth here. There can be slight mistakes like this. Anyway, please understand, by substituting the effective depth or overall depth here, there will not be much difference. Very minor difference only will be there. So we have our overall depth as 130 millimeters. Please do understand that. And here we have 111 millimeters. So anyway, let's proceed with this value, 0.151 percentage. Now what we can do, and if you remember what we have done in the previous problem, so we have calculated the actual area provided, we have the percentage of steel reinforcement. So as per figure 4 in the IS 456, so below the control of deflection, we are provided with, say, let's go to that. That will be better. So, I think it was in page number 36. Yeah, here we have that. Okay, so this was the condition. We will be assuming that the control of deflection criteria will be satisfied once we are assuming the span to effective depth ratio. And for cantilever, they have suggested a value of 7. Okay, but as per this condition, depending on the area and the stress of the steel for tension reinforcement, the value in A or B shall be modified by multiplying the modification factor obtained as per figure 4. This thing we have seen in the previous problem, that is why I am going fastly. So if you move on to the figure, we have a figure like this, and to refresh things, here we have percentage tension reinforcement, here we have our modification factor, then we have different curves corresponding to different stress in the steel, and these stresses are Fs is equal to 120, 145, 190, 240 and 290. And to calculate the value of Fs, we have the expression here 0.58 times Fi into area of cross section of steel required to the area of cross section of steel provided. Now coming back to our slide, we are using the same equation. Substituting the value of area of steel required was 154.42, and the value that is provided is 167.47. Substitute the values here and find the value of Fs. So once you get the value of Fs, what do you have to do? You have to, from this curve, you have to, based on the percentage of steel and the Fs is 230, so it will be somewhere between these two curves. This is 190 and this is 240, so it will be in between these two curves, in between or very near to that of 240. And based on the percentage of tension reinforcement, in this case percentage was 0.151. So this is 0.2, so it will be somewhere here, 151. Okay, so you just go up and take the corresponding modification factor. So in this case, they have taken the modification factor as 2, almost at the top point. So here 1.5, and they have just gone up, and they assume that it will be intersecting somewhere here. So they have taken the modification factor as 2. Approximately, you can take the modification factor based on your visual inspection. Okay, so in this case, modification factor is 2. So based on control of deflection, L by D requirement in the initial clause was 7. So you have to multiply this by 2. So that is coming around 14. Now from this ratio, if you are again calculating the effective depth requirement, you can see that this is coming around 89.29 millimeters only. So basically our assumed value of D effective depth was 111, which is safe. So basically it satisfies the condition for control of deflection also. So our total design is safe here. Okay. So this was regarding the design of primary reinforcement. Hope it is clear to you. Is there any confusions or any doubts or any area which need further clarification?
Sir, L1.3 കിട്ടിയില്ലായിരുന്നു അത് ഒന്നുകൂടി പറയാമോ?
Okay, sure. So basically it was our clear span is given as 1.25 meters, right? Now, as per the condition given in the code, say once you have a cantilever like this, the code suggests that the effective span in this case will be this 1.25 means it is the clear distance, that is this one, the distance from this end to the face of this support, this one. Okay, now the effective span L effective is equal to this value plus depth, effective depth by 2. That is what code suggests when we have an independent cantilever. Okay, this should not be a part of a continuous slab or continuous beam. In that case, we can consider it independently, and in that case, this condition applies. That is 1.25 plus effective depth by 2. So this will be basically equal to 1.25 plus 0.111 divided by 2. So it will be coming around something like 1.305 or something like this. So I just took it as 1.30. Any more doubts? Is it clear?
Yes, sir.
Yeah. So if it was a part of a continuous slab, things will change. In that case, not in this case, if this slab should be considered as a continuation of a continuous slab, so sorry, what you have to do is that you have to things will be different. You have to L effective, in that case L effective will be equal to this 1.25 plus, suppose you have a support here, so basically in that case you will be having a support here and you will be having this slab continuous. So suppose this width is, say, let's assume it to be 250. So in that case it will be 0.250 divided by 2, because it is a distance, this value plus half of this distance, so from center of the support to the free end. That is what code is suggesting. So in that case L effective will be like this, but in our problem we are considering it as independent cantilever, so our L effective will be 1.30 as shown in this. Okay, now coming to the calculation of secondary steel. So you know that secondary reinforcement must be provided as 0.12% of the cross section. So when you consider the cross section, you have to take, say, and this is another important thing, but this will play more importance when you consider two-way slabs. Okay, in this case it is okay, but in the other way, sometimes it may be different. So when you provide the secondary reinforcement, the primary reinforcement we actually provide in this direction, and when you provide the secondary reinforcement, you have to actually consider this cross section. Okay. So here you will be having a width of say 1000 millimeters, and this depth is capital D. Okay. So based on this, you have to actually calculate the AST requirement, and again try to provide the same diameter bars in both the directions. So 8 millimeter diameter. So based on this, you have to calculate the spacing, and you have to check for the maximum permitted spacing also. So below the same clause, you have conditions regarding secondary reinforcement, spacing of secondary reinforcement also. That was what I remember is around maximum permitted values for 50 millimeter center to center distance, or for 4 or 5 times the thickness. Okay, so you please cross check that, and you provide the reinforcement at the required center to center distance. In this case, it is coming as 8 millimeter diameter bars at 300 millimeter center to center. Clear? Okay. Now again, the check for shear. So we have to perform this check actually. So first thing is that you just calculate the value of tau v. Tau v, we have already calculated the factored shear force, and it was obtained as 9850 newtons. So by the width into the overall depth, so the width is 1000 into the overall depth, that is 130. So this will come around 0.08 Newton per millimeter square, or MPa, 0.08 Newton per millimeter square. Now you already have the value of PT also. We have already calculated in the case of span to depth ratio. When calculating the revised span to depth ratio, we have already calculated the value of PT, and it was obtained as 0.151%. And based on this PT, that is 100 AST by BD and the grade of concrete, we can get the value of tau C from table 19 of IS 456, and also get the value of tau C max, and compare these values. And here you can see that the value of tau C is coming around 0.364. Okay, 0.364. And why I have multiplied using 1.3? If you remember back, there was a table. Let's firstly go through that. 40.2.1.1. 40.2.1.1. Okay, so here for solid slabs, so please see here, for solid slabs, the design shear strength for concrete shall be tau C into K, where K has the values given in the table, and here the overall depth of the slab is given, and our slab is having an overall depth of 130 millimeters. So it is basically this condition, 150 or less, and our factor is 1.3. So we have to multiply 1.3 with the tau C value obtained from table number 19 of IS 456. So from table number 19, we are obtaining a value of 0.28, and therefore final or the actual tau C is 0.28 into 1.3, which will come around 0.364 Newton per millimeter square. Okay, or 0.364 MPa. So this value, so when compared to tau v, you can see that tau v is less than tau c by 2. Half of, even when we consider half of tau c, tau v is further lesser. So we need not provide shear reinforcement again as per the suggestion from IS 456. These things we have already seen, right? So basically our design is complete. Now what you have to do is that you have to provide the detailing. Okay, so I think we have the diagram here. So one cross section along is shown here. So basically this is a cantilever slab like this. So we have a fixed support here. Then we have to provide the reinforcement on top as we have designed here, and this is your secondary reinforcement. Okay, this red one is your secondary reinforcement, and the other one on top is your primary reinforcement. Okay, so basically from primary reinforcement we have seen that it was 8 mm at 300 millimeters center to center. In this particular problem, we have obtained the secondary reinforcement also as the same, that is 8 mm at 300 millimeter center to center, and we have to show the clear span as well as the width of the support and the overall depth provided. Then one more thing is that we have to calculate the value of, what was this thing? This was your development length, which should be calculated in the case of a cantilever beam. So again, we have the equation LD is equal to, so from the code you have the corresponding equation, and we have already seen how to calculate the value of LD. By substituting these values, you just find the development length required and extend this main bar through the required distance like this. And you have to show it like this, like drawing this diagram and mark the dimension as 376.10 or maybe 380. So provide it as 380 millimeters. So this will complete your design. So basically this final detailing will also have a credit for your examination, and in some cases you will be asked to draw the detailing alone. Say for 5 marks, normally in the university examination they used to ask, show the detailing of a cantilever slab or show the detailing of a cantilever beam. So what we have to focus is that you have to provide, if it is a slab, you have to provide the main reinforcement or the primary reinforcement on top, a secondary reinforcement below that, then you have to show the development length and the other dimensions. If it is in the case of a beam, what you have to show is, so again, if it is the case of a beam, you will be again having this main reinforcement like this, and the development length will be provided here. Okay, this is your support. Here also you will be having a support. So this will constitute your development length, and this will constitute your main reinforcement. So in addition to this, you will be having a stirrups holder. Then you have to provide the stirrups. In the case of a beam, cantilever beam, it will be like this. Then you have to show the details of all these things. See, so this will be basically something like 10 millimeter, not like this, 2-legged, 10 mm5 at some spacing, some maybe 150 mm C by C. Arbitrarily you can give some values. Then regarding the main reinforcement, say 2 number of say 16 mm Y. Regarding the stirrup solder also you have to, so the arrow must be like this, pointing the actual ring, not like this. Okay. So this will be, say, maybe 2 number of 10 millimeter fibers as stirrup solder, and you show the depth of the beam with the clear span and other things. Okay, so this is how you have to provide when it is asked for 5 marks.